Aloha, Richard Halverson here. This is ITS 228, and today is January 26th, and we're in week 3. Let me share my screen. And so we are in week 3. Let's look at the syllabus. We are we should be covering sorting algorithms today, this week and next week. That's good because we should catch up a little bit. I haven't had a chance to talk to you much yet about algorithm analysis, and you know, this course is there's a lot more concepts, understanding the concepts, you know, really understanding the concepts rather than being able to whip out a bunch of complicated code. It's kind of more important that we learn how to look at code and analyze code and figure out how long it's going to take based on how much data is fed to it. You know, and just understanding those concepts better than more than the sort of, you know, rigorous programming that we try to focus on more in 128 and 148. So anyway, let me just mention I did post assignment 2. Assignment 2 is it's due in a couple weeks. Of course, as you know, in this with me, since this stuff is all auto graded, I try as hard as I can to make things auto graded. Then I can accept late work, not really late, I guess late work up until the time I have to turn in a grade, because it's a matter of running the program. But anyway, this program here is I have you take a look at this top 5 salespersons algorithm that was presented in chapter 1. And basically what it is you pass it a list of salespeople that have their names and the amount of sales that they did. You pass this program, this method, that list, and it will print out the top 5, you know, as far as sales go. So that's what this does. That's what this algorithm does. And so what I ask you to do is you'll notice this algorithm is written in this algorithmic language that is sneeze. That is somewhere like in between C or Pascal or some language, and you have to convert it into Python. And the tricky part of this problem is this line right here, sort descending. So the way this works is it keeps track of the top 5. It has this array that keeps track of the top 5, and what you do is you go through all of the salespeople that come through, and you compare one by one with the lowest one in this sorted list of 5. And if this new salesperson is bigger than the lowest one, then you replace the lowest one with this new salesperson and resort the list. So for each person, you may end up resorting the list, but the list has only five records in it. It's a short list. So anyway, what you're going to do in 2.1 is you're going to paste. You're going to enter in this program. You're going to go to your server, create a new file, paste this in, and this should run. So what this does is this loads up an array of people with sales, and it prints it out, and then it calls the method, and the method will run here. And this method doesn't do anything right now. All it does is print out nothing. Okay, so it initializes the array. Then there's a bunch of code here that you have to translate from here. See here, we initialize the array. This is the code you type in. You convert that to Python. And then here, this is the ending part, which displays it out. I've already converted that to Python for you. So there we go. There's the Python to initialize the array it's going to use. You type in the code here from here, the bolded part, and this prints it out. So you should be able to take this program as it is right now without this part here, and it should run with no errors, except for it just doesn't print out the top 5 because it doesn't do anything. And so once you get your code in there and running, then it should print out the top 5, of course. Okay, so you're gonna do this twice. You're gonna create a program, top 5 salespersons, and you're gonna create another one, top 5 salespersons 2. The only difference between the two is for the first one, you are going to implement this line right here, this sort descending. You're going to implement that with one Python statement, and that is this right here. Okay, so that actually does that sort in descending order. It sorts this array of top sales in descending order based on whatever the total sales is. Okay, this is so you don't have to understand this yet, but in fact, I tell you to, after you get this in, you should go do a Google search on Python sort list of dictionaries. How do you sort a list of dictionaries in Python? It's a good Google search because it explains this. Now, our textbook doesn't even cover this, but it covers 2 other ways. But anyway, so the first one that you write here, you're gonna create this code in Python, but this line right here, this is the line that's going to take care of that. Okay. Now, the second one here, instead of using this line, instead of using a fancy Python sort method, you're going to actually incorporate this part of an insertion sort. So we're going to learn about insertion sort this week and next week, because we're going to cover sorts. Probably this week we're going to learn about all different kinds of sorts. One of them is insertion sort. And insertion sort, the inner part of insertion sort is exactly what we want to do when we are executing this algorithm, and we've just added this new record and we want to sort in descending order. So right here, you're going to put this, because that'll insert it up. Now, I've just given you a brief summary of what this assignment is. Over the next this one, probably two more next week days. Sometime during there, I will be, covering more of this to make sure you can get through it. All right, so you're gonna create this program on your server, and again, you can use. Did I put the link in here for the grading assistant? Yeah, the grading assistant here now is ready, and you can debug the 2 ones here. So I've done them. And so this is what the first one looks like. Now, there's a reason why I'm doing this. I want to briefly go over this conversion of an algorithm to Python. This should be a really automatic thing for you to do, and I'm going to show you the conversion for this algorithm. I'm going to show you the conversion, but it's going to be in just a form on the screen that would be difficult for you to copy paste. You're going to have to look at it and copy it over. But here it is. And it's this portion right here, not this line here, not this line, that's something different. Not this line, these are comments. It's actually this, it's actually, you know, this down to here. And here's that top sales sort lambda line that we're talking about. And this thing just loads up this top sales array with empty records like it says to do. And this thing simply checks the next salesperson. It's going to go through all the salespersons. It's going to go through all the salespersons. It checks each one by one, checks to see if it has greater sales than the last one in this list. This list is sorted in descending order, 0, 1, 2, 3, 4. So number 4 is going to be the one with the lowest sales. And see, this list contains the top 5. So it's the top, the second, the third, and the fourth, and the fifth. So number 4 contains the 5th highest, and then that's all this thing holds. And so as you go through, you just need to take a salesperson, a new one, compare it with the bottom one. If this new salesperson is bigger than the bottom one, then replace the bottom one with this new one and resort. And where the resort will make that bottom one fall into the position that it should, you know, in the order of sales. All right, so that's that. And so this thing runs, it makes sure that there's a lambda there and a sort there. And I got an error here. I got an error here on purpose. Oh, yes. Oh, look, so this thing contains an error here. This code contains an error, whatever. But anyway, and what it is, because I wanted to test an error. And the error is, it doesn't display this out in descending order. It displays it out in ascending order. You notice these are go up. These go up. And that's not what, you know, that's not what this does. This is sorted in descending order. And so the very top one is the highest one, and number 4, 0 through 4 is the lowest one. Anyway, this displays out the opposite. So I got an error saying the list elements are correct. In other words, these are all correct list elements. It checks that, but it's not in descending order. So I got, I guess I got a point for it or something. Anyway, I don't think I got any points. I think this should be +0. So anyway, because I only got 7 points out of 10. So that converts to, there's 40 possible for this one. For the other one, it's 60. All right, so for the second part here, you're gonna stick that in there. You're gonna convert that. Oh, here it's already Python, so, except for you're gonna make this be top sort. And that might be all you need to do. All right, so let's go back to the syllabus. Now, this textbook, of course, is really good, and it's designed where you don't really need me to learn it. In fact, this course, if you take ICS 211 at Manoa, they do this flipped format, classroom format, where, you know, you learn all this stuff on your own, and then when you come to class, we go over programs and so on. You know, that's not a bad way of teaching, but I like to just present, just go over the pages that you're going to have to read more carefully, just so you kind of get an idea of what you're supposed to get out of those pages. So we've searching algorithms. We looked at binary search. We looked at linear search and binary search. And in fact, let me just real quick here go and see. I didn't make this a link yet, did I? Shoot, I should make that a link. sucks. The link is in the email that you get every week. That's the correct link. So we are ITS 228 spring, where it's this one. And the last video was, oh, okay, good. We did cover linear and binary search. And by the way, anyway, it's a good one. So this is what you do when you're, when you're, it comes time to study and maybe you haven't watched all the videos and there's a few videos you want to watch. You don't need to watch other videos. You can just very quickly, as you scan through the video, this is good because when you scan through the video, right up at the top, you can see where, where I am most of the time. Here, see, now I'm on 2.2 binary search. So if there's things that you need to learn there, and here I'm going over the first assignment. So you can just like skim right to here, and there's the code right there, type it in, and so on. So that's why. And what I do is I want to see how far I got. It looks like I got to. Oh, here I'm explaining the assignment because you're supposed to do some kind of. You're supposed to implement the recursive binary search in this assignment. Anyway, so that's how far I got. Okay, so that's binary search constant. Okay, so let's go through 2.4, 2.5, 2.6, 2.7, because that's where we introduce to this computational complexity, this concept of computational complexity, and this kind of separates the computer scientists from the programmers, kind of, I guess. I don't know, not really, but understanding computational complexity helps when you are designing new algorithms to let's say you're designing a game and you have to generate all the future probabilities of certain paths taken, and so you generate this tree, or maybe it's actually a graph because you can come back to the same point again. And then you want to compute how to traverse through the tree in a certain way. That's where this kind of stuff. All right, so there's constant time operations and constant time. Oh, it's all about worst case. It's all about worst case, and it's all about how much longer does the program take to execute when the data grows. So if you double the size of the data, does it double how much time it takes for the algorithm to execute? Does it make it does it make it 3 times it, or does it not really add any time at all? Okay, so it's answering those kinds of questions. Constant time operations. And you're kind of counting steps. You're counting steps in the program, and it doesn't need to be any more granular or accurate than that, because really what it is you can always get a faster processor. So for you can 2 years from now you're going to be able to execute it 10 times faster because the processors are going to be that much faster. But so we aren't talking about that level of performance. We're talking about the difference when the difference in performance as you increase the size of the data. So here, constant time operations like this, each step here takes the same amount of time, presumably. Not really, this takes longer than this, but still it's constant time. For non-constant time operations here, like for example this loop here, that depends on x. So the bigger the x is, bigger x, the more this thing takes, the longer this time takes. In fact, if x is twice as big, it takes twice as much time. This also, because when you concatenate one string to the end of another string, you have to at least go through the whole first string. You have to get to the end of the first string before you can sort of attach on the second string. And in this case, if this is Python, for instance, strings are immutable, so we're have to create a new string anyway. By the way, you can make it a constant time operation depending on the data structure you use also. So we're going to get more into that. But in some cases, linked lists are a more efficient way to store data, because if you need to do things like this, like connect, add lists together, if they're linked lists, then you can get to the back of the list in one step, as opposed to if they're arrays, consecutive memory locations in the memory, and you want to combine two together, you have to move a bunch of data around. So this makes sure you understand the concept of constant time operations, and identifying constant time operations. They're just addition, subtraction, multiplication, referring to something, referencing something, doing comparing two fixed size data values, and so on. These are all just constant time operations. Now here's functions that growth of functions and complexity. There's the upper bound and the lower bound, and you shouldn't be scared off by these equations. They're just it's all, you just have to pay attention to the biggest term. I mean, here we have to pay attention to the 3n squared because it's bigger than the rest of them. N squared is bigger than n and bigger than nothing, and so on. Come up with an example here. Well, let's just say that an algorithm with the lower bound, let's say a lower bound is the best case time equation. Let's see, what's a good example? Okay, a good example is linear search, where if you're looking for see, that's not a good example because it's well, okay, yeah, it's a linear search. The best case is one. It just takes one comparison, because if what you're looking for is the first item in the list, then you only have to look at that one. You don't have to look at any more. With the binary search, it would be if the first item is exactly in the very middle of the list. But it's better. This sort of analysis is more meaningful when we're looking at sort routines, for example. There's some sort routines, sorting, where if the data is almost all sorted and you run the sort routine on it, it doesn't take very long at all. But there's other kind of sort routines, there's other kinds of sort methods or sorting algorithms, where it doesn't matter how well sorted, how close to being sorted the data is to begin with, it still is going to take the same amount of time, or about the same amount of time, to do the sorting. So sorting is a good example of where you want to, depending on the nature of the data, you may want to choose a different sorting algorithm depending on that. So I'm going to come back to this concept a little bit later, because it actually applies to the assignment 2 also. But just know that for a particular algorithm, depending on the data, there can be a worst case time. There can be a worst case set of data, and there can be a best case. An average case, of course, is somewhere in between. And there are Greek symbols for these measures, or these equations that we're talking about. O O provides a growth rate for the algorithm's upper bound. Omega is for the algorithm's lower bound, and I'm not sure what that theta is. That theta? Theta, yeah, theta is the growth rate for both the upper. It's an equation that it captures both the upper and the lower bound. So and and here we're you really only need to understand the rules of how you combine the two equations after they're given to you. Okay, so this is the best case and this is the worst case. And so which function, and if the function is only like one term like this, would be the lower bound for the algorithm. I think is it, let's just look here. You can, is it this one? Yes. And for which is the upper bound for the algorithm? Is it this 5n squared? I don't know. It could be. I'm gonna say this, but it could be 12n squared. Let's see. No, it's got to be because when n is 1, it's when n is the same. When n squared is the same as n, then we end up adding the 2 and it ends up being 12. So it's this one. Anyway, so you can look through that. Luckily, there's not going to be any exams on this. It's just concepts. You have to understand these concepts. Okay, so let's say we have the steps of the algorithm, you know, and it's counting loops. It's loops within loops. Here's a loop within a loop, plus another loop, plus some initialization step at the beginning or some step at the end. Okay, so there's like maybe this stuff is only in the outer loop. There's the outer loop, and then there's an inner loop inside, and that's what this is, and that's kind of how you determine these steps, and that's kind of what we'll get good at in sorting routines. In most of the simple sorts, there's a loop, there's an inner loop and an outer loop, and so we have something that's like this, n squared, because for every execution of the outer loop, the inner loop goes through an entire, you know, from beginning to end, and then there's another one beginning to end. So if you have the beginning to end on the outside times the beginning to ends on the inside, and you end up with that squared. So so when you look at something like this, you would just know that the big O is the n squared term, and you don't care about the coefficient. You don't care about any of these smaller terms. You only care about the biggest n, the n with the biggest exponent. And so that's what it is. So it's O of n squared. Okay, so you can make sure you understand these concepts. There's composite functions. There's a pattern to it. You look at the pattern. Okay, but these are all the different growth rates of for these algorithms that we talk about. You know, there's regular n, where as the data grows, and n is the input size, or the number of data elements that the thing is going to process. As n grows, the amount of time that it takes to execute the growth rate in time just goes along right along with it. So if O of n is just n, then if for an input of 10, it takes 10 microseconds. For 50, it'd be 50. For 100, it's 100, and so on. For log to the base 2 of n, you see it's much smaller, and that's what a binary search is. If you're doing a binary search on a list of 100, and you increase it to 1,000, it's only going to take twice as long. Yeah, twice as long 1028, yeah. Right, just 2 to the 8th power, or 2 to the 7th power is about 100, and 2 to the 8th power, no, it's going to take 4 times as long. Yeah, because it goes in the power of 2. So anyway, but from, let's see, from 100 to 1000 would be 128, 256, 512, 256, 512, 1024. That's 2 to the 8th times more. It's 8 times. And then from 1000 to 1000 to 10,000, and from 10,000 to 100,000, each time it doubles. It doesn't double in time. It only goes up it only goes up logarithmically. So anyway, so there's and then there's n squared and n cubed and so on. So n squared is what typical sort algorithms are. So you know, if so you see that when n goes from 10 to 100, we're going from 1 millisecond to 1 second. Okay, so that's 1,000 times more. And then when we go to 1,000, we're going up into the minutes. We're going to 10,000, we're going up into the days, and so on. So and then when we get up to where the n is actually an exponent, then that's the one that takes the longest. And so this is the kind of thing where if you have to try all possibilities. Here there's some sort of shortcut, but here is an example of where, so if you have a graph, if you're visiting, you want to visit all the say you have a bunch of cities that you have to visit, and there's highways or flights between the cities, and you want to find the shortest path to all the cities. That's the kind of thing where you have to try all combinations, and so it's O of 2 to the n is what O of n is, and that's not polynomial. This is polynomial. This is exponential. And when they talk about NP complete problems, that's what they're talking about. They NP complete problems, or problems that take 2 to the n amount of time. They haven't been able to prove that there's not a polynomial time algorithm to solve it, but they haven't been able to find a polynomial time algorithm to solve it. So anyway. So here's a nice graphing tool which shows you you can see how these things grow. This is n log n, this is n squared, this is 2 to the n. Oh, this is n factorial, this is the highest growth. All right, so here's some other examples as far as, and we have common algorithms. Let's see, this goes for another half an hour. So here's a constant time algorithm. We want to find the minimum between two numbers. It just takes the same amount of time no matter what. Here's a binary search, which is O of n log n. And you know, as you double the size, you know, as the size of n increases, the amount of time that it takes to execute just increases by the log of n. And O of n is linear. This is like for a linear search. If there's a million items, you may have to look at a million items to find the smallest one, or to find one that you're looking for, to find the particular one you're looking for. Here it's log to the base n. No, it's log to the base 2 of n, and that's because you can. First of all, it's got to be sorted, okay? And by the way, if it's not sorted, it's going to take at least O of n log n to sort it. So you better be searching for a lot of different items, a bunch of them, if you're going to take the trouble to sort it first. But if you do take the trouble to sort it first, then you can search for any one of them and find it in log of n time. And that's because it's sorted, you can start in the middle. And if you look in the middle, you're not only looking to see if that's the one, but you're looking to see if it's not the one, is it in the top half? Is it higher or is it lower? And when you answer that question, then you're automatically eliminating half because you're eliminating the side that it's not in. So each time you look, you cut it in half. Now this also means that you're able to get at the middle in the same amount of time. Okay, so it also assumes that if you have an array of 1,000,000 items, to find the middle one, it's sorted, to get to the middle one, or to get to any of them takes the same amount of time. So you can randomly access any element in that list in the same amount of time. So it assumes that also. Anyway, so this is the difference between binary search and linear search. And then we start having the sort routines, the faster sort routines, merge sort. The reason merge sort is O of n log n is because you end up dividing it in half and sorting each half, and each half takes well, anyway, so it's another one of those divide and conquer algorithms where you keep sorting the halves, and then once you have two halves that are sorted, to merge those two halves takes O of n. Yes, that's right. So if you have two sorted lists, to merge those into one sorted list takes O of n or O of 2n. It takes because the algorithm is you take the top one each time you take the top one and add that to the new list. So you look at the two, take the top one, add it to the list. Look at the two, take the top one, add it to the list. And so you're able to get through. You're able to merge two sorted lists in O of n time, or O of 2n time. And then and you divide up your single list into halves each time. So anyway, it ends up being O of n log n to do a merge sort. To do a selection sort is we've learned that it's you probably learned that from 148. It's where, first of all, you go through, you find the biggest one, let's say you're searching from smallest to biggest. You go through the list, you find the smallest one, you take that one out. And you add that to the list. And then you go and you look at again to find the smallest one, and you take that one out. You add that to the list. And then you go back and you look through the list again, you find the smallest one, and take that out. So each time you find the smallest one and you remove it from the list, and what's left over is the remaining items. And so as you can see, for each item in the list, you have to go through the whole list. So that's n times n. So for each item, you have to go through the whole list. So that's n times n. So that's why it's O of n squared. So it's not quite n times n, because each time you're going through the list, you end up being smaller by 1. But when you do all those equations, those T of n equations, it ends up just reducing to O of n log n. And then Fibonacci is exponential, where the n is in an exponent. And you can kind of look and see how this grows even faster than this. All right, so that's O notation. This helps you understand the differences between there. And then this is this algorithmic analysis, where we look at an algorithm, and based on the nesting of the loops, we can come up with an algorithmic analysis, and we come up with this O number, this O notation. So if there's something going on where we keep on dividing something in half, dividing the set in half, that's usually some sort of log term. And if we're seeing nested loops, it's usually some sort of n squared term. And if there's just some stuff in the beginning and some stuff in the end. Those are constant things, and they don't add to the computational complexity. The O of n. Okay, so here we're talking about nested loops and so on. All right, so those are good concepts to learn. Recursive definitions. This is 228, so we should understand, you know, how recursive algorithms work, you know, what they are. We're going to learn more by doing, because when we get into traversing trees, it's easy to understand the concept. It's easy to write recursive algorithms to traverse trees, and it all kind of makes more sense at that time. So we can sort of just know that with a recursive function, it's a function that calls itself, and it doesn't have to call itself directly. It can call something which ends up calling itself again. And so in a recursive function, knowing that it can be coming back again, calling itself, there has to be something which will end the recursion. And so, when you write a recursive algorithm, a recursive program, you usually make sure that gets put right up on top. And so as n comes in, and we see that n, each time we call it, n gets smaller for sure. And it takes n to get smaller. And then when it's called, we have a stopping point where when n is equal to 1, we don't call ourselves anymore. We return. And so this returns, and then that starts the cascading of the returning, because then this returns, comes back around, then which makes this return, which makes this return, and so on. And we end up coming out of the recursion. But these are some examples of how you can take regular functions that you might normally, and you can always implement a recursion function as an iterative function. It's just that with recursion, it's sometimes it's easier to think of it as a recursive function. Problem with teaching recursion is oftentimes we end up trying to teach you recursive concepts with functions that you might probably not do recursively anyway, and then you're twisting your mind around trying to understand what recursion is. But when we get into traversing binary trees, you'll really see it. Plus, binary search is a pretty good one also. It helps you to kind of see the concept of recursion, which is kind of why I had you do this. In the first assignment, you're actually implementing a Python version of this. And I guess there is no Python version of this in the textbook, but of course you can always just search Google Python binary search, and you know, pop up right away. Here is one, because it's calling itself. And then there's the iterative one, which just loops. So let's see what time it's almost 12. Okay, so let me go back here, and okay, good. So I've covered the concept of big O notation, and we will learn more about big O notation, because I will bring it up, and it'll be brought up through the rest of these, where we're learning these different common data structures that advanced programmers use to keep track of stuff. All the stuff they have to do, all the stuff you do, it's all basic, boils down to about 10 different algorithms that operate on about 10 different, different types of data structures here. And that's what this course is. You're going to be exposed to all of them, and you're not going to necessarily be handy with all of them. But in the future, you'll scratch your head and say, "Oh, that's right. I bet you a B tree would work for this." And then you go look up B trees, and you go, "Oh, that's right." You remind yourself that way. Now with with sorting algorithms, here we're basically just going through and covering all of the different types of sorting algorithms. There are these O of n squared ones, which are selection, insertion, and shell. Let's see, it tells at the end. It does. Oh no, this is okay. Here's a list of the sorting algorithms that we're learning. A selection sort, as I just explained. Insertion sort is where you should go over insertion sort, because that's the one I have you implement in assignment 2. Shell sort is a different kind of a sort, and I never really learned that when I was growing up, but it's there. Quick sort is kind of an interesting sort, and it's n log n. You're splitting, dividing by 2. Merge sort I talked about already. The thing about merge sort is you have to have twice as much memory around when you're doing the merging. With these other ones, you're just exchanging, so you maybe at most need a constant amount of extra memory. With merge sort, you need an O of n amount of extra memory. Heap sort is, I've talked about heaps. They're very interesting. It's a heap is a data structure. It's like a tree where every parent, let's see, a max heap. Every parent is at least as big or bigger than either of its children. It's got 2 children, right? It's a binary tree. So each parent has 2 children, and the value of the parent is always greater than or equal to either of its children. So that means when you have this huge heap, it's got a bunch of children, but you know that the very top node is going to be the biggest one, and so okay, so there's that. And then also if you to restore a heap, okay, so for the heap sort, you pull the top node off because that's going to be the biggest one, and then you take the very last node at the very end and you take that and you put that at the top. Okay, and then to reheap that only takes log n, because basically you're just bubbling that when you put it at the top, you're bubbling it back down in place, and there's going to be a new top. Okay, so and that only takes log n. So again, you're pulling it off. If you have 100 items, you pull off 100 of them. That's the n. And then for each one you pull off, you got to reheap it, and that's only takes log n. So that's why heap sort is n log n. It takes n log n amount of time to complete. And then a radix sort is a different kind of sort. Or you can see what that is. But a lot of these, like an O of n sort, there's a lot of overhead, a massive amount of overhead, so it might not be worth it. So you should look at all the different kinds of, look at all these different sorting algorithms, and there are Python versions of them. That's what's nice about this book here. Here's this is the Python version of selection sort, and make sure you understand that, and you should try to learn the difference between these sorts, go through the exercises, but you don't have to write code, but you are going to code some of them, and in fact you're going to encode. This is insertion sort. Here is you go, this is the outer loop, so you go through each one, and the top half, the top part of the array is the sorted part. So so when you start out, we have 3, and that's only one element, so that's sorted. And then you take the next one and you insert that into the top half. And when there's 2, and by inserting, it bubbles up. It bubbles up to the point where it's in its right position. So if we're sorting in ascending order, this is already sorted. Let's run through this, because this is what you're going to do your assignment on. Okay, so first of all, we started out at the very one, and the 32 is the first one, so 32 is sorted already. and then we're going to insert in 6. 6 is greater than 6 is less than 32, so they're going to exchange places. The next one, 15, is going to exchange places with 32, but it's not going to exchange places with 6 because it doesn't have to. And then 3, so okay, let's just keep moving here. So it goes through another iteration, and 15 gets inserted into its proper place, and this is temporary location here. Okay, keeps on going. It's keeping it. Okay, so the next one now is 3 is going to get get inserted. So it's going to exchange with 32, and then it's going to exchange with 16, and then it's going to exchange with 6 because it has to get inserted all the way back up to its place. And by the way, this is the same algorithm that you're going to implement in assignment 2, because you're going to go through these top salesmen, and this is here we're sorting a list in place. In your assignment, you're actually just you're taking each one of these and you're adding it to a new sorted list, which just keeps track of the top 5. But it's the same idea. You're gonna take one of these, you're gonna replace the bottom one, and then it's gonna bubble up. And I use the term bubble. I shouldn't use the term bubble because there's something else. There's another sort called a bubble sort, which is similar, where you're just exchanging. But here you are. Now with insertion sort, you don't really need to exchange as you go up. You can pull out, and move a bunch of them, and then put the one in its place. Let's see what this one does, because we're going to see the 3 move all the way up to the 6, and 32 is going to move down 1, 15 is going to move down 1, and 6 is going to move down 1. So we're doing 3 now, and 3 and 32. That's gonna 3 goes over there, 32 goes there. Oh, okay, they do exchange. Now it's going to do 3 and 15. 3 goes over there, 15 goes over, 3 goes there, and then we're going to do 3 and 6. 6 is going to go over there. 3 goes over there, 6 goes over there. Okay, and then we're done. The last one we do is 20, and 20 will bubble down. We'll exchange with 32, and then it's done. All right. So this is the and in your assignment, I ask you to take this while part and implement it in the. And this is not Python. Do we get a Python version of insertion sort? Yes, we must, because that's what I. Just make sure you understand that. Here's Python insertion sort. So yes, I'm just asking you to take this part and putting it in your new thing, but it's not. They're not called numbers. It's called top sort, and that might be all you need to change. And oh, here J gets initialized as I, and in your thing it's going to be initialized at 4 because each time it's 4 items to be shifted 4. All right, so that's that. 38, 238. So that's binary. That's insertion sort. Quick sort I'd say this is like the most complicated sort of all the common sorts. Quick sort is a very common sort. When you're using the Python sort methods, it'd be interesting to look and see what actual sort methods they used depending on the data. And what likely happens is depending on the data, it will choose a different sort method. And I don't know which one it uses and when it uses which ones, but anyway, so this is a quick sort is, it won't do me any good to try to explain this to you because I'll just confuse you. So this is something you should probably try to step through and try to understand. All right, that's quick sort. this is the Python version of quicksort. If we had more time, I'd actually ask you to implement some of these things. I may ask you to, at some time, I may pick some important algorithms here that you should probably actually have some experience writing a little bit of code, getting it to execute, that sort of, you know, helps you remember it more. And so quicksort, quicksort is a good one because it's one of those sorts where it's not something you'd probably come up with on your own. You know, the other ones you can kind of think of how you might come up with a lot of these on your own. You know, even merge sort, which is a good one. But not any of these other ones. Here we covered this, the comparison between the two. Let's see. Okay, so these here is this section is very close to our assignment, the second assignment I gave you, and in fact, I was going to actually have you implement the two uses of the sort and sorted methods and functions that are built into Python. I was actually going to have you implement one or both of these. I decided to have you implement the sort in two ways other than these two, but these it's important that you go through these two examples, and I may go through them more again as I talk more about assignment 2, because here we're using the key function, because in this example here, in this section, we are sorting a list of sets. No, tuples. We're sorting a list of tuples. And I could have had you represent assignment 2 as a list of tuples, because we're storing the name of the person, the name of the salesman, and the amount of sales they had. So I could have used a tuple where the first item of the tuple is the name, and the second item of the tuple is the sales, kind of like here. But I didn't. I'm using dictionaries. So so each item is a dictionary, and of course a dictionary is not, you do not refer to the elements of the tuple. You refer to the elements of the tuple by an index. You refer to an item. You refer to an item in a dictionary by its index, or by its named index. Okay, not by the number index, but by a key, which is a name, a word, or something. So in this here, we are there's two ways. There's this using a custom key function, and here we're specifying, and I'll have to go over this again, but this is kind of a weird way of specifying the key. So we're using the sorted function. This sorted function returns a sorted list. It's going to sort a list. It returns a list. So this is a list. Name result is going to be a list. It's going to be a list, same form as this. This is a list of tuples, and so the sorted function, the first argument is the thing you're going to sort, and the second argument, this key, specifies what you're going to sort on. Now, if this was just a list of numbers, a list of numbers, then you can just say, I don't even think you need to specify the key then if it's a list of numbers. No, you don't. You don't need to specify the key. But here you have to specify which part of the element is the thing you want to sort on. And so, and the way you do that is you say key equals something. Well, this is actually a function which identifies, which indexes which element. So key is name is actually the key is name, and this is the element that comes in. It's going to be, this is the element, this is the element, this is the element. So what's the key? Well, it's the 0th one. It's the index, so it's going to be this one. So key by name is going to be the index 0. If it's key by ID, then it's this one, and it's going to be the index number 1, which is the second one here. And in our assignment, we are doing, in our assignment, we are, each element is a little dictionary. It's a little dictionary here. And what kind of hints do I, here I give you, okay. So lambda, this is just like, this, a custom key function. Except for this custom key function, it's not all done in here. It's defined out here by using this. Lambda is the same kind of thing, and you can do a Google search here and you can read about it. But here we're doing the same kind of thing. So this is the element that comes in, and this is how you index. This index is what the key is. Okay, and so here this is indexing the key because we want to sort on sales total, just as this is indexing the key. Okay, now this is just a 0, 1, 2, 3, 4 index. This is an actual name. Why? Because that's how you specify, one of the elements in the dictionary. You specify one of the elements in the dictionary by a name. You specify this is what we're sorting on, and this how do you refer to that? Well, by its name. And in this case, what are you sorting on? Well, it's the first one there, and so it's this first one here. That's how you reference that. Anyway, so there should be kind of a pattern there. You can kind of pick up on that. In this class, I remember when I first started taking computer science classes, I was an electrical engineering major, and a student, the math was too hard, so I took my first computer science class, and it was it was actually a 3-level. It was like a 3-level class back at the University of Minnesota where I took it, and we didn't write a lot of programs. We figured out these kinds of things, these algorithms, and you end up trusting your instincts a lot, and same with even when you're writing algorithms, they don't have to be exact. When you're coding a program, it's got to be exact. You got to have the colon in exactly the right place. But when you're writing these algorithms, they don't have to be exact. You're just expressing like the idea, what's being looped, what the loop is, what the for loop index variable is, and so on. And so that's why it does good to look for patterns. And that's kind of what I'm trying to encourage you to do here. We explain it. It's explained in this section, but we're kind of taking it one step further because we don't have a list of tuples. We're doing a list of dictionaries, and these are the elements of the dictionary, and they're getting appended onto the list and so on. So anyway, I hope some of this made some sense. And are there any questions?
Sir, thank you very much.
All right. I will see you. There's another class this week. I can't remember if it's tomorrow or the next day, but I'll see you then. All right. Thank you.
Awesome. Tomorrow. Thank you.